Good morning, everyone. I'm Sebastian Galliani, and I will be chairing the keynote session by Francesca Molinari. Francesca is the workshop professor in the Department of Economics at Cornell University. She received her PhD from the Department of Economics at Northwestern University. Francesca's research is in the area of econometrics, both theoretical and applied work. Her theoretical work is concerned with the study of identification problems and with proposing new methods for statistical inference in partially identified models. Today, she will present her study on discrete choice model with heterogeneous preference and consideration. She also works on the analysis of decision-making under risk and uncertainty. Francesca is currently serving as joint managing editor at the Review of Economic Studies. Francesca will now present uninterruptedly for 45 minutes, and then we will devote the last 10 minutes of the sessions to questions and answers. Please type your questions and comments in the Q&A box, and those will be sent to me, and I will select some of them to present to Francesca at the end of the session. I want to thank the organizers for putting together a great academic program. Now, Francesca, the floor is yours.
Thank you so much, Sebastian, and thanks to everyone who is participating in this session. It is a great pleasure and an honor to talk with you about our research. And let me begin with saying that this is joint work with Victor Aguiar at the University of Western Ontario and Levon Barsegian, who is my colleague at Cornell. And as it was announced, the topic of this presentation is discrete choice analysis when one has both heterogeneous preferences and heterogeneous consideration. And of course, I will provide details on what do we mean by this. So the basic motivation for our work is the following. If you think about discrete choice analysis, and you think about the textbook approach to discrete choice analysis, the basic idea rests on a principle of revealed preference. So we observe consumers choosing one alternative out of a finite set of feasible available alternatives. So imagine that there are 100 products, and we observe the consumer choosing one of these products. And from seeing, let's say that the consumer chooses product 1 out of 100 products, we conclude that the consumer receives a higher utility from product 1 than from all other products. And by observing many different consumers and observing variation in the observable characteristics of the consumers and of the alternatives, we can figure out the distribution of preferences. And this idea dates back very much in the past. And of course, one of the most popular models in this line is the McFadden's model in the logit family. Now, typically in the textbook, we presume observation of each individual's consideration set. In fact, actually, the textbook presumes that all individuals consider all 100 alternatives which exist in the market and chooses the one that gives them the highest utility. In practice, however, the collection of alternatives that the individual chooses from may change across individuals, and in particular, it may be unobserved by the researcher. Why could it be unobserved by the researcher? Well, there are many, many reasons why that could happen. One possible reason is a simple missing data problem. So, for example, there are budget of liquidity constraints or agent effects that the researcher does not observe. And because of this budget or liquidity constraints, not all alternatives are available to a given consumer. Think about purchasing an automobile. Not all automobiles available in the market are actually available to a given consumer. For example, a given consumer may not be able to spend more than a certain amount of dollars on the purchase of a car. And then it could be, on the other hand, it could also be because of behavioral reasons that the individual does not consider all the alternatives. So, for example, the individuals may have limited cognition or may proceed in their choice in following elimination by aspects type models, where you're only going to consider, let's say, electric vehicles because you care about the environment, or models of satisficing, salience, simultaneous and sequential search, choice overload, rational inattention, are all mechanisms through which there is going to be heterogeneity in consideration sets across consumers, and moreover, this heterogeneity is going to be observed by the researcher. So what happens if you follow the textbook model and you assume homogeneous and either observable or full consideration sets? Well, what's going to happen is that if you estimate a discrete choice model, assuming that the individual considers all 100 alternatives, I'm going to use this idea of 100 alternatives as my sort of working example to which I'm going to keep going back to, okay? And these 100 alternatives are all the cars that exist in the market. If you assume that individuals considers all the 100 alternatives and that the one that you observe that individual choosing is the one that maximizes their utility, but in reality, the individual only considers a subset of these 100 alternatives, then you're going to obtain inaccurate inference on preferences. So your estimates are going to be biased. And as your estimates are biased, your welfare analysis is going to be biased, and your counterfactual analysis is going to be biased. Moreover, in conjunction with standard assumptions, for example, from the models in the logit families, but not only, assuming full consideration sets and homogeneous consideration sets may lead to a failure to rationalize many phenomena that we observe in real data. The phenomena that I've listed here are mostly coming from the industrial organization literature and include violations of Slutsky symmetry and of absence of nominal illusion, zero shares for non-dominated alternatives and large shares for dominated ones, violations of the assumption of the independence of irrelevant alternatives, complex substitution patterns, upward sloping demand, and one could keep going on and on with lists of features of data that cannot be rationalized by standard models. So now the question is, what are the challenges presented by models of limited consideration? To talk about these challenges, which are going to turn out to be both on the identification side and on the computation side, let me start with the textbook discrete choice model, where I have a feasible set calligraphic J, which is going to include my 100 alternatives of my working example. And I'm going to call capital J the total number of alternatives. Again, it's 100 in my example. And I hope everyone can see my cursor here moving around. The data that we observe, the choice of the individuals, can be summarized by the shares of the choice probabilities of each alternative. So what we observe from the data is the fraction of individuals that choose alternative J. Here, Y is going to denote the individual's choice. J is going to run, little j is going to run from 1 to capital J, so from 1 to 100. And I'm going to observe these shares across all 100 alternatives, and these shares are going to be conditional on certain observable characteristics. Here I'm going to denote by Z characteristics that change with both individual and alternative, by S individual demographic characteristics and other characteristics that change only with the individual, and by X individual characteristics that change only by alternative. And the idea of the standard discrete choice model is that the individual chooses alternative J if the utility that the individual derives from alternative J is at least as large as the utility that the individual derives from any other alternative K. And that is true for all K in the feasible set calligraphic J. And here I'm assuming that we're working with a random utility model. So I'm going to integrate out the unobservable random part. Eventually, I'm going to come to you with a random coefficient model. So here I'm using this notation F calligraphic U as a sort of shorthand that I will elaborate on as I move into the talk. And think of this as the distribution of the random coefficients. And this distribution is going to be conditional on some of the observable characteristics, but not all, because of course I'm going to need some characteristic to be excluded. So some characteristic to be independent of the random coefficients in order to have any hope for identification. And so in the end, what we're going to have is a total of capital J equations of this form, and we know that we obtain point identification if these capital J equations, which of course have to hold for all x, s, and z, are going to have a unique solution. Now, what happens in the case of heterogeneity in consideration set? What happens is that each individual, in fact, draws a consideration set that I'm going to denote by capital bold CI. And this consideration set is going to be a subset of the universe of feasible alternatives. And now the left-hand side of my equation remains the same because I continue to have the same observable data. The problem that we're going to be facing here is that we don't observe this capital CI. It's not in the data that the researcher observes. And on the right-hand side, I now have a new model predicted probability of the individual choosing alternative J. And what this model predicted probability boils down to is that I need to now sum over all the possible realizations of the consideration set CI that include alternative J. And so now, inside the integral, I continue to have an indicator of whether the utility of alternative J is at least as large as the utility of the other alternatives K, but now instead of running over all the possible alternatives, I only run it over the alternatives that are inside the realization capital K of the consideration set CI, and then I'm going to weight that event with the probability that in fact the consideration set realizes equal to K. And then of course I'm going to again integrate out the random coefficients. In general, I continue to have these J equations, which have to hold for almost all values of S, X, and Z. But now these equations, in general, no longer suffice to point identify both the distribution of preferences and the distribution of consideration sets. Why does that happen? Intuitively, think of an extremely bad scenario where everybody's consideration set realizes equal to a singleton. In this case, the choice data that we observe is completely silent about preferences because individuals chose the only alternative that was in their consideration set. The standard textbook example presumes, the standard textbook approach presumes that the consideration set realizes equal to the feasible set with probability 1. The reality is somewhere in the middle. We have heterogeneity in consideration sets across people. And if we do not observe the consideration set, we have a pretty formidable identification problem to address. And that's what we're going to do in this paper. From the computational perspective, before I move on to tell you what we do in this paper, from the computational perspective, I want to attract your attention to the fact that we also have a challenge because now, if you think about writing down the model implied choice probabilities, those involve this summation over all sets K that include J. And so generally speaking, we're going to have a summation that grows exponentially in the total number of alternatives, capital J, which are in the universe of existing alternatives. So also from the computational perspective, this problem is challenging. So what do we do in this paper? What we do is to propose a semi-non-parametric model of limited consideration. The model is going to be semi-non-parametric because I'm going to come to you with a parametric utility function, but then which is going to have random coefficients. And the distribution of these random coefficients is going to be left non-parametric. And also the distribution of consideration sets is going to be non-parametric. And in particular, one key feature of our approach, which is also kind of distinguishes it from most other related work in the literature, is that we're going to allow for dependence between consideration sets and preferences. And we're also going to allow for dependence between consideration and regressors. I'm going to first show a set of results which has some exclusion restrictions with respect to some of the regressors. And then I'm going to show you more general results that allow dependence with all regressors, but this dependence, part of this dependence is going to be structurally specified, because if you have completely unrestricted dependence between consideration and all regressor, we showed in a different paper that you're going to have partial but not point identification. And the model that we put forward is able to, that single model is able to rationalize all the data features that are listed on the previous slide. So the absence of Slutsky symmetry, absence of nominal illusion, violations of absence of nominal illusion, and so on. The type of result we provide is non-parametric point identification of the joint distribution of preferences and consideration sets. And we do so using cross-sectional data on choices and observable covariates. If one has panel data, one can obtain non-parametric point identification under weaker restrictions, but we don't do that in this paper. The identification result that we propose leverages first a pure random coefficients model without additive errors. I'll talk more about that, of course. Second, it crucially rests on rich support for a regressor that is independent of preferences. And this actually is going to mimic the type of assumptions that we make also in models with full consideration. And thirdly, as I will explain in detail in the next couple of slides, it leverages the substitution patterns of the choice probabilities with respect to the exogenous regressor. And we also show that the computational cost in certain instances of our model may grow polynomially in the number of alternatives, in the number of total alternatives in the feasible set, rather than growing exponentially. Let me first give you, I'm going to try to give you an intuition for what we do multiple times throughout this talk, and this intuition is always going to be the same, but as I keep going, I give you more and more details for how it comes across. So our idea is going, as I showed you before, as I argued before, the basic equations that relate the model to the choice probabilities do not suffice for point identification. We need to use something more. And what we're going to do is to exploit information on how the choice probability for alternative J, for example, changes with respect to, so this Z is going to be the exogenous regressor that the preferences are independent of. For concreteness, I'm going to refer to Z as a price, but it does not need to be the price. So the price that the individual I faces for alternative J. And we're going to look at how the share of alternative J changes with the price of alternative K, alternative L, and all the way to alternative capital J. Why would that be helpful? Why would it be helpful in this context to look at how the share of good J changes with the price of good K, L, and capital J? The idea is that for you to observe a change, we're going to look at the higher order partial derivatives, and for you to observe that the share of the derivative of the share of alternative J is sensitive to marginal changes in the price of alternative K, L, and all the way to capital J, you need three key ingredients. First, the individual has to be indifferent between all these alternatives. That's going to tell us something about preferences. Second, all these alternatives have to be in the individual's consideration set. Otherwise, the choice probability would not change with the price of an alternative that is not in the consideration set. And lastly, there should be no other alternative in the consideration set that is preferred to alternative J, because otherwise alternative J would not be the one that is chosen. Put together these three things, these three features are going to inform us both on consideration and on preferences in a way that allows us to pull those apart. And so what we show is that under mild restriction, this intuition suffices for point identification of the distribution of preferences and distribution of consideration sets that depend on preferences. So what I'm going to do today is to show you a simple example and then to talk to you about the semi-non-parametric identification result that we derive, both in a baseline model where consideration is independent of this exogenous regressor Z that I'll keep talking about and over and over again about this Z regressor, and for a case where consideration is dependent on this regressor Z, but under some structure. I will not have time to talk to you about the computational feasibility and show you Monte Carlo simulations. I will try to talk to you briefly about the comparison with the logit family, and if I can, about related literature, and then I will conclude. So here is my simple example to set the stage. In all discrete choice literature, we assume that the outcome variable that we observe, yi, is the one that maximizes the consumer's utility, uij. The twist in this paper is that we recognize that the consumer may not maximize their utility over all alternatives in the feasible set in calligraphic J, but may only maximize their utility over a consideration set CI that I don't observe. For simplicity, in the slides that follow, I'm going to assume a simple form for the utility function, where the utility function is going to depend on the observable covariate on the observable covariates that are alternative specific, xj, on the regressors, on the exogenous regressor zij that changes both with individual and with alternative. And it's going to depend on random coefficients beta I, which may be a function of the individual specific characteristics as I. For example, think about an instance where people of different ages have a different distribution of the random coefficients. So across different ages, people care in a different way about engine size, okay? If we think about the case of purchasing a car. And here, if you think of Zij as a price, the coefficient of Zij is normalized to 1, and the way that you interpret these random coefficients beta I is that this is willingness to pay of individual I for characteristic J, okay? So a crucial assumption that we're going to maintain across our entire work is that the random coefficients beta I, so these are the preferences, are independent of the exogenous regressors Zij for all J, conditional on individual characteristics Si and alternative characteristics X. So again, the distribution of preferences may change with S and X, but it cannot change with the exogenous covariates Zij. Ci here is our consideration set. And for this part of the talk, we're going to weaken that assumption later. We're going to assume that Ci is independent of these regressors Zij across all J, conditional on the individual characteristics, the good characteristics, and importantly, conditional on preferences. So the consideration set distribution may in fact depend on preferences. What the researcher observes is Yi, Zi, Si, and X. So the chosen alternative and the covariates, but the researcher does not observe the consideration set. I'm going to show you a simple example where there is a total of 4 alternatives and where is a total of 2 random coefficients. The choice of this number is first of all driven by the fact that this way I can make a simple picture. The fact that the total feasible alternatives is larger than the number of random coefficients is basically a rank condition that we need to carry throughout. And so we always need the number of feasible alternatives to be at least as large as the number of random coefficients plus 2. And the reason is because we need to identify the distribution of the random coefficients. We only have utility differences. So we, even in a model of full consideration, we would need at least m plus 1 existing total number of alternatives. And in addition, we need 1 more alternative to basically trace out the distribution of consideration sets. And in what follows, I'm going to slim down notation. I'm going to suppress the conditioning on S and X. But again, I want to emphasize both the distribution of preferences and the distribution of consideration sets can change with individual and alternative characteristics in arbitrary ways. Now, if you look back at the top of the slide, I'm going to, here I am going to introduce the notation that I'm going to use on my pictures. I'm going to denote by beta tilde ik, the product. So, you know, we have that the individual I chooses alternative 1 if and only if the utility that individual gets, from alternative 1 is at least as large as the utility that the individual obtains from any other alternative k for all k in the consideration set. And so what I've done here is simply to write in a convenient way these utility differences. And then I'm going to call the portion of the utility that depends on observable characteristics that change only across alternatives and that are multiplied by the random coefficients. I'm going to call this portion of the utility differences beta tilde ik. And I'm going to call the portion of utility differences that pertains to differences in the exogenous regressor as zeta tilde ik. Okay. Now, as I said before, I'm going to look at how the share of alternative 1 is going to change with the price of alternative 2 and the price of alternative 3. Because I'm going to look at that partial derivative, the only realizations of the consideration sets where, in fact, there is going to be variation in the share of alternative 1 with respect to the price of alternative 2 and the price of alternative 3 are realizations that include 1, 2, and 3. And so my pictures in the next slide are only going to look at consideration sets that include all these 3 alternatives. Of course, I could look at the share of how the share of alternative 2 changes with the price of alternative 1 and 3, or 1 and 4, and so on. And then I would go through many different combinations of possible realizations of consideration sets. And the last key ingredient for our approach is the following. What we want to do is to identify the distribution of preferences evaluated at some b, a possible realization of the preferences. And what we are going to do is to assume that there is, for that value of b, that there exists a value of this exogenous regressor z and an open ball calligraphic z superscript o around that value, such that at this value little z, the individual is indifferent across all 4 alternatives. Okay. What does it imply that I'm assuming that I have this value of z at which the individual is indifferent across all alternatives? What that really means is that identification in this paper is going to be based on local variation of z. And if the variation is only local, we're going to be able to identify preferences locally to this value of z. And if the variation, if instead z has full support, we're going to be able to identify the distribution of preferences and the distribution of consideration sets everywhere. If we are in the middle, where there is a continuous variation in z, but only locally, then we're going to have partial identification, where the identification is point identification locally to those values of z, and where we don't have sufficient amount of variation of z in the middle, we're going to only obtain partial identification. Okay, so what do I plot in this picture? This picture plots the coefficients in the space of the preferences, beta 2 tilde, beta 3 tilde. It plots the vertical line here is the indifference, is the values of beta, the realizations of preferences, where the individual is indifferent between alternative 1 and alternative 2. And to the right of this vertical line, the individual prefers alternative 1 to alternative 2. The horizontal line is the indifference point between alternative 1 and 3, and above it, the individual prefers alternative 1. And the diagonal line is the indifference point between alternative 1 and alternative 4, and above it, the individual prefers alternative 1. The left-hand side panel is going to plot the situation where the choice set with the consideration set realizes equal to 1 to 3. The right-hand side of the panel depicts the situation where the consideration set realizes equal to 1 to 3, 4. With a total of 4 alternatives and 2 random coefficients, these are the 2, and given that I'm going to look at how the share of alternative 1 changes with the price of alternative 2 and 3, these are the only 2 relevant realizations of the consideration set. Now, because in the left-hand side panel, alternative 4 is not drawn in the consideration set, the indifference point between 1 and 4 is irrelevant, and so I've removed it from the picture. Now, I've highlighted here in gray the areas over which of possible realizations of the random coefficients where the individual is going to choose alternative 1. And additionally here, there is a formula that in fact depicts the probability, the integral that you would need to take. Here I'm implicitly assuming that preferences have continuous distribution, and in fact that there is a well-defined density function for this distribution of preferences. And so here I have the formula that if you take that integral, in fact, you would obtain in the left-hand side the probability that alternative 1 is chosen and the consideration set realizes equal to 1 to 3, and on the right-hand side the probability that alternative 1 is chosen and the consideration set realizes equal to 1 to 3, 4. Okay, now here is what I'm going to do. I'm going to make alternative on the right-hand side panel. I'm going to, in fact, evaluate my choice probabilities at the vector z. Think about the vector of prices, where the price of alternative 4 has been made a little bit more desirable compared to the indifference point that I started with. And I can do that because I have an open ball around this value of z that makes the individual indifferent across all possible alternatives, okay? Now, and so when I do that, when I make the price of alternative 4 a little bit more attractive, the area where I'm going to choose alternative 1 is going to shrink. If you compare these two pictures, what you see is that the diagonal line has moved up, and so alternative 1 is chosen a little bit less often, okay? And now I'm going to take a derivative. First, I'm going to take a derivative of this choice probability of choosing alternative 1 with respect to the price of alternative 2. And when I do that, that highlights this blue line, both on the left-hand side and on the right-hand side. And what is this blue line? Is the locus where the individual is indifferent between alternative 1 and alternative 2, okay? Because that's where you will, on the margin, respond to a slight change in the price of alternative 2. And then I'm going to take a further derivative with respect to the price of alternative 3. When I do that, on the right-hand side, I actually zoom into this red point. That's the point where the individual is indifferent between alternative 1, 2, and 3. On the left-hand side, when I do that, I actually get a 0. Why? Because I've made the price of alternative 2 slightly more, of alternative 4 slightly more attractive. And when I do that, there is no region left where the individual is indifferent between 1, 2, and 3. Because that region would be here, this original crossing point that is now no longer feasible because the price of alternative 4 has become a little bit better. If you apply a simple Leibniz rule to the formula inside my integral here, you're going to obtain that what this second order derivative identifies, because keep in mind that the left-hand side is data, okay? It identifies the product of the probability that the consideration set realizes equal to 1 to 3, with the density function of preferences evaluated at our value b that we're interested in. And then this determinant of x tilde inverse is simply something that I need to keep around, because in here I did because at some stage I did a change of variables. So you can sort of safely ignore it because this is data, except that there is an assumption here that the alternatives are sufficiently distinct from each other that in fact this inverse is well defined. Now what I'm going to do next, compared to the picture we had here, now I'm going to make the price of alternative 4 a little bit less attractive. I'm going to increase by epsilon the price of this alternative. When I do that, my indifference point between 1, 2, and 3 is now back to being feasible. And so when I take the second order derivative of the share of alternative 1 with respect to the price of alternative 2 and alternative 3, that derivative is going to identify the sum of the probability that the consideration set realizes equal to 1 to 3 plus the probability that the consideration set realizes equal to 1 to 3, 4, multiplied by the same identical value of the density as before, multiplied by the same identical determinant of x tilde inverse, which I need for from my change of variables, which is the same value as before. What does this mean? What this means is that by looking at the substitution patterns of the shares of my 4 alternatives with respect to the price of 2 of the other alternatives, I'm going to be able to identify the probability, the product of the probability that the consideration set realizes equal to the feasible set multiplied by the density function evaluated at this b that I started with, as well as the the probability that the consideration set realizes equal to each of the possible consideration sets that exclude one alternative for each of the possible alternatives. As I will show you in a few slides, this identifying up to this common constant f beta evaluated at B, density function evaluated at B. All these consideration sets, the full one, the one where you drop one alternative, if we had additional alternatives in a feasible set, the one where you drop two, the ones where you drop three, and so on and so forth, is going to suffice to identify the entire distribution of consideration sets. And once we have identified the entire distribution of consideration sets, we can go back to recover the density function. Again, what's the intuition? The intuition is that the reason why the share of alternative 1 is changing with the price of alternative 2, 3, and so on is because the individual was indifferent between alternative 1 and alternative 2, 3, and so on, and all of them were in the consideration set, and moreover, no alternative which gave a higher utility was in the consideration set, okay? Now, let me formalize. This is the basic idea for how identification goes. Now, let me formalize a little bit. As I stated before, our first assumption is that we have a random sample of individuals' choices, where the assumption is that the individual chose this optimally from their consideration set Ci, which, however, Ci is not observed. And then we observe this Zij, which when I drop the subscript j is because I've collected them all in a vector, which is an individual and alternative specific attribute. And then the researcher observes Si, which are the individual specific attributes, think age, gender, and so on. And Xj, which are the alternative specific attributes. And again, when I drop the subscript j, is because I'm looking at the entire vector of the entire matrix of alternatives across all alternatives in the feasible set. Now, the second assumption is that the utility function has this simple linear form. From now on, I'm going to suppress the dependence of beta I on Si, but the distribution of beta I can change with both individual characteristics and with the characteristics of the goods. Here, I want to emphasize, because I know this is important in empirical applications, that while for my simple example and to try to make all of this easier to explain, here I'm taking a utility function that includes no unobserved good characteristics. In fact, in the paper, which is still, we're still writing a draft, we can allow for unobserved characteristics Xij. In fact, we're going to allow, in the current version of the paper, we allow for a single unobserved characteristic Xij. And this Xij is going to have its own random coefficient alpha I. And we're going to be able to establish identification of the joint distribution of alpha I and beta I, and to allow the distribution of consideration sets to depend on both alpha I and beta I. Okay. Moreover, we can also allow this Zij, our crucial exogenous regressor, to enter the utility function through an unknown function Hj, which of course we're going to need to restrict. We're going to need to make certain location and scale restrictions, both on that and on the alpha I distribution. But this more familiar model is something that we can handle, and for which, in fact, we do have identification results. Beta I is going to be assumed to be distributed according to some distribution, to have a CDF capital F of beta, which again can depend arbitrarily on individual characteristics and alternative characteristics, and that this CDF has a density function little f of beta, which is what we directly identify. And lastly, this assumption number 3 is crucial, and we never drop it throughout our paper. And you also need this assumption in models with full consideration, is that beta I is independent of the exogenous regressor Zi, conditional on the individual characteristics and the goods characteristics. Our next assumption, which I've used actually in the pictures that I showed you before, is that the consideration set is independent of Zi, of this exogenous regressor, conditional on individual characteristics, good characteristics, and importantly, conditional on beta I. So again, one more time, we do allow the distribution of consideration sets to depend on preferences. And we and this assumption, because I may run out of time and not be able to show you formally, but we, in fact, in the second part of the paper, we substantially weaken this assumption that the consideration set is independent of ZI through an idea of a budget constraint, where if you think of ZI as prices, we're going to allow that individuals draw a budget constraint, so total amount of money, let's say, that they can spend on the purchase of goods in this category. And then they are going to, based on that draw of the budget constraint, they are going to form a budget feasible set, which is going to be a function of the prices of Zij for all J. And then they're going to draw their consideration set from this budget feasible set. Okay, so we can substantially weaken this assumption one. Assumption two that we have says that, and this goes back to what I tried to emphasize while showing you the pictures and so on, that if we can identify up to a common multiplicative positive constant, which in my example was the density evaluated at B, the distribution of the consideration sets for realizations K of size at least as large as number of random coefficients plus one, this reveals the entire distribution of consideration sets. In the next slide, I'm going to show you several examples of consideration set formation processes where that's the case. We could weaken this assumption by replacing with a requirement that for realizations of the consideration set, which are of size smaller, less or equal than number of random coefficients, the distribution of consideration sets does not depend on beta. And we can also weaken it by requiring full support in Z. If we have full support in Z, we can substantially weaken this assumption, but that's kind of pretty technical and I'm not going to show it today. Sorry. So let me show you a few examples of where this crucial assumption, our only restriction basically on the distribution of consideration set, this idea that if I identify it up to positive constant for realizations of size greater or equal than number of random coefficients plus one, then I've identified the entire distribution of consideration sets. First, an example which is often used in marketing is what is called alternative specific random consideration, which, however, we substantially generalize by allowing dependence on the random coefficients. And what this model says is that each alternative J has its own probability, phi J, to be in the consideration set. Again, this can depend on observable characteristics S and X and on random coefficients beta I. And then the key assumption is that the probability that the consideration set realizes equal to K is equal to the product of the probability that each alternative in K in fact realizes inside the consideration set, multiplied with the product that each alternative little k that is not in capital K does not realize inside the consideration set. So here the crucial assumption is an independence assumption, which says that each alternative has an independent probability from all the other alternatives of being in the consideration set. If you make this under this model, which, as I said, is used very, very often in marketing, if you can identify the distribution of consideration set up to common multiplicative constant for K equal to the entire feasible set, and for K equal to the entire feasible set minus one alternative for each of the capital J alternatives, then by taking the ratios of those probabilities, so the common multiplicative constant drops out, you're going to identify the phi J for each J in the feasible set. And once you have the phi J for each J in the feasible set, you have the entire distribution of consideration sets. Another example also commonly used in IO and marketing is the sleeping agent or inertia example, where the individual either pays no attention whatsoever to this choice problem, and then that means that the only alternative in their consideration set is the default D. Think about retirement or pension plan choice or health plan choice, where if you don't choose anything, then you get the default. That's equivalent to saying that your consideration set realizes equal to default, or the individual chooses to pay attention to the problem and then considers carefully all calligraphic J alternatives. Again, in this case, our assumption from the previous slide is satisfied. And the last example that I'm going to talk to you about is that of a minimum consideration set size. And then in that case, the idea is that any consideration set of size below this minimum is going to have probability 0. An example where that's the case is in school choice problems, where if individuals provide a ranking of more than one alternative, then the minimum, if all individuals provide a ranking of more than one alternatives, then the minimum consideration set size is basically the number of alternatives that they have ranked. And if that number happens to be at least as large as number of random coefficients plus 1, then our assumption is satisfied. And the final assumption that we make is a rich support assumption, which basically says that across any values of the other observable characteristics, Zi has positive density on some set calligraphic Z, capital calligraphic Z, where, as I said before, if this is just local variation, then we're going to identify our density locally. And if instead this Z superscript J is, say, for example, Rj plus, so if we have full support, then we identify everywhere. And here I listed some examples from the empirical literature where, in fact, we do have observable characteristics which have arguably large support. The question, of course, this list does not guarantee that my crucial assumption of independence from preferences is satisfied. This would be for the applied researcher and for the reader to decide whether they believe that they're satisfied here, although I will emphasize one more time that even if you have full consideration, you still need this type of assumption, okay? And then, as I mentioned, with these assumptions in place and an assumption which pertains to invertibility of this X tilde, which is basically saying that rank condition is satisfied, and so which basically says that the alternatives are sufficiently distinct in their observable characteristics, then we have our identification result, where again, one more time, we allow for the consideration sets and the preferences to depend on each other. I think that I have 5 minutes. Is that right?
I think we still have 10 minutes.
Okay.
But I mean, we left, as long as I don't have questions, I'll let you go until the end. Okay. Otherwise.
So, and this slide, what I want to show you briefly in this slide is this idea of allowing for dependence between also consideration sets and these variables Zi, our exogenous variables, think of them as prices. So to be a little bit more formal about this budget constraint idea, the idea is the following. You mentioned that individuals I draws some zeta I, where zeta I is distributed according to some G, which can again depend on individual characteristics, alternative characteristics, and on preferences, okay? So this zeta I represents the budget constraint for choice for this type of items. And the idea here is that, again, this G itself has a continuous CDF, which has a density little g, okay? And now, armed with that budget constraint, the individual determines their budget feasible set, Ji of zeta I, which is going to be comprised of all alternative k, for which Zik is less or equal than zeta I. Again, think of Zik as prices, zeta I as the maximum that the household can pay for a car, for example. And now the individual draws the consideration set from this budget feasible set, and conditional on the budget feasible set, the consideration set is independent of the prices of the Zi's, but keep in mind that dependence on the price of all alternatives is at play here through the formation of this budget feasible set. And then we're going to assume that the most expensive alternative in the budget feasible set is in fact in the consideration set with probability 1. And the reason why we need this is because we're going to identify the distribution of the budget constraint. To do that, we're going to have to be able to trace it. And if the most expensive alternative is not in there, obviously we cannot trace its distribution. We can only get bounds of that distribution in that case. And then the remaining assumption is basically the same as before, on the same restriction on the consideration set. And again, under these assumptions, we can identify the joint distribution of the budget constraint and of the preferences, and the distribution of the consideration sets conditional on preferences and on the budget constraint. Let me also take a minute to talk to you about computations, because as I explained at the beginning, computations are a big deal here as well. So how computations are going to go here is the following. I'm going to define a set calligraphic B subscript J, which is going to collect all alternatives K, which give a higher utility than alternative J, okay? And then I'm going to call calligraphic QJ to be the probability that alternative J is in the consideration set, and no alternative that gives higher utility than alternative J is in the consideration set, okay? With that, I then know that the probability that alternative J is chosen, conditional on the realization of preferences, is in fact this QJ, because you choose alternative J when J is in the consideration set and nothing better than J is in the consideration set. And so then I can integrate out this calligraphic QJ with respect to distribution of preferences, and that's going to be giving me my choice probability. This itself indicates that I don't need to enumerate all consideration sets. I need to enumerate only a subset of those. But this can further dramatically simplify under my first example of a consideration set formation mechanism, the one with alternative specific consideration, where each alternative has an independent probability of being in the consideration set, because in that case, the choice probability boils down to the product of the probability that alternative J is in the consideration set, and that all the alternatives K, which give a higher utility than alternative J, are not in the consideration set. Okay, and so in this case, the computational cost would grow only polynomially in the number of alternatives. And then one can use Monte Carlo integration to compute the choice probabilities. We do that in a simple example. I'm not going to go through the details of the DGP here. What I want to tell you is simply that we did it with 3 random coefficients, 30,000 observations, and the feasible, this D, I apologize, should be a capital J here, feasible set which is size 13, 26, or 39. Again, I apologize. We took a base number, doubled it and tripled it, and we compared our results with those from a pure random coefficient model with full consideration, which of course is misspecified in this case because we generated the data with limited consideration, and from a mixed logit model with full consideration. And first thing I'm going to tell you quickly is that in fact our computational time grows polynomially, as you can see from this graph here, in the number of alternatives. Of course, it is slower than a pure random coefficient model or a mixed logit model because we estimate many more parameters. But in terms of accuracy of the estimator, this table reports true values. So here in the BGP, we use 1/2 for beta 1, 1 for beta 2, and 0.15 for beta 3. And the random coefficients were independent of each other and had a variance of 1. And as you can see, using our method, we recover these parameters pretty accurately, while of course both a pure random coefficients model and a mixed logit model exhibit very large biases because those models are misspecified in this case. And this bottom table simply shows that we also recover quite accurately the correlation between preferences and consideration parameters. I'm now going to jump a few slides because I want to leave you with a quick comparison with models in the logit family. So let me actually talk to you about the nested logit because that's a little bit easier to explain. What happens in the nested logit is that the researcher forms a partition of the set calligraphic J of, so the universe of feasible alternatives, and those are divided in disjoint nests of similar alternatives, which I'm going to denote by capital K with subscript R, and there is going to be a total of capital R such sets. And then if you think about McFadden's nested logit model, it tells us, under the standard assumptions in the logit family, it tells us that the probability that the chosen alternative belongs to nest little r is some function of the utilities, and that the probability that alternative J is chosen, given that the chosen alternative is nests R, is some other function of the logit family. And what I'm going to argue to you is that the nested logit itself is a limited consideration model. And the same is true for the mixed logit, but I don't have time to show you that in detail. And what type of limited consideration model is that? Is a model where CI, the consideration set, is restricted to take on only realizations capital KR. And if that's the case, then the event that the chosen alternative belongs to KR is equivalent to the event that the consideration set realizes equal to KR, because the chosen alternative has to belong to the consideration set CI, and CI in the nested logit is assumed to realize equal to one of the KR, and this KR are disjoint, so these two events are equivalent. And so what the nested logit does is that it specifies the conditional distribution of the consideration set in a parametric way. I will skip the slide of related literature, except to tell you that this is not a new problem. We have not come up with a new identification problem that people had not thought about before. We are addressing a question that has plagued the discrete choice literature since at least the 1950s, and it's a very active area of research today. The most important aspect of what we do, in my opinion, is that we allow for this arbitrary dependence between consideration sets and preferences. As far as I know, these are the only 4 papers in the literature that also allow for dependence between consideration sets and preferences. And doing so, allowing for dependence between consideration sets and preferences, in my view, is crucial because, for example, this type of dependence naturally arises in search models and models of satisficing, as well as in rational inattention models. So I'm now completely out of time. Let me quickly summarize. What we do is to provide the semi-non-parametric identification results for the joint distribution of preferences and consideration sets, allowing for dependence between consideration sets and some regressors, and using only cross-sectional data on choices and observable covariates. How do we do that? We use a pure random coefficient model without additive errors, and we exploit an exogenous regressor which has rich support, similarly to the type of support assumptions which are made in homogeneous full consideration models. And we exploit the substitution patterns with respect to this exogenous regressor. The method is computationally feasible, and in general, it avoids the need to enumerate all possible consideration sets. And in practice, the cost may grow polynomially in the number of alternatives in the feasible sets. Thank you so much for your attention, and please send me comments and questions.
Thank you, Francesca, very much for this great presentation. We are just on time, so I think I close the session. Bye.
Thank you so much, and yes, please send me questions if you have any.